Welcome to the God Academy podcast.
Hi everybody! Hi, not Gil, because Gil isn't here. Gil was taken out of his house by a Shinbet drone who told him,
"Come quietly or there will be trouble."
Because he wasn't sufficiently enthusiastic about the new political realities in Israel. But Gil is a smart guy and he'll understand soon enough which side his bread is buttered. So he'll be back and I'm sure totally fine. Meanwhile, it's me, your host, Rutger Vos, which is not a corona symptom. That's how you pronounce my name, in fact. And I'm gonna see if I can do a nice episode on my own.
Let us see what Squirt does flying solo.
So, buckle up. So, what are we talking about today? Well, it's a Science in Movies episode. There's 3 movies, and what we have started to do, or at least what we've been discussing behind the scenes a little bit, is to try to make these episodes a bit more like, as if there's a point to them. So we're trying to work towards some sort of narrative. And the narrative this time is about the use of malicious code injection to defeat the enemy. And what do we mean by that? Well, Nazis, men hunting hybrid raptors, space locusts, and the coronavirus are all enemies with which we cannot live together. It's either us or them. And because we are supposed to be intelligent organisms, one way in which we might try to defeat them is by manipulating the underlying code that makes them tick. So here's the thing. Gradually, probably, over the course of the last 200 years or so, we have discovered a couple things, namely that underneath nature, which I guess 200 years ago we thought was this natural world, it's very, continuous, valued, not somehow discrete and encoded, is actually underneath it all something that is organized in pretty rigid systems. Starting out, let's say we begin with this romantic idea of nature. So we might start with romantic poets like Lord Byron, who thought of nature as this sort of kind of the way we experience it, unpredictable, irregular, soothing, perhaps.
There is a pleasure in the pathless woods. There is a rapture on the lonely shore. There is society where none intrudes, by the deep sea and the music in its roar. I love not man the less, but nature more.
Why do I start with him? Well, he had a couple of daughters, and one of them is Ada Lovelace, who is the first computer programmer, in fact. She programmed algorithms on this machine developed by Babbage. She worked with him. And she developed a kind of algorithm for generating Bernoulli numbers. And so all of a sudden there was this idea, at least in science and in our own abstractions, that we can construct these symbolic languages and manipulate them and do operations with them. But roughly at the same time, actually very close in time, this same kind of discreteness was also gradually being discovered in nature. So, for example, Ada Lovelace published her first paper in 1843, and then that was 4 years after Darwin had written his story of the voyage of the Beagle, and then in 1859 he actually, then published The Origin of Species. And then shortly thereafter, in 1866, Gregor Mendel did actually something that Darwin hadn't really cottoned on to. So Darwin still kind of thought that heritable information is this very continuous kind of blending inheritance thing. Like, you have something that's blue and something else that's red. Well, I guess the offspring must be purple, right? Blend. But Mendel actually did experiments with peas in his garden. And he looked at the different traits of the peas, but for example also at the color of the peas. And there was like a green and a yellow variety. And he did various crosses. And what he wasn't seeing was kind of like greenish yellow or yellowish green. No, there was green and yellow in very predictable ratios across generations. We didn't fully understand what that meant. But that was the first beginning of genes as discrete packages of information and not something that you just blend. And another guy with a similar name, not Mendel, but Mendeleev, was 3 years later publishing his first papers about how there's actually the same kind of discreteness in chemistry, right? Mendeleev is, of course, the sort of inventor, or however you want to call it, of the periodic table of the elements. And he kind of discovered that different chemical elements have very discrete, valence, like charge in electrons and atomic weight. And there was some sort of regularity in it with metals and gases and so on. And that actually started then and has continued to develop further and further, both in computing and our insights there, and which is all very discrete coding, and in biology. And of course, then biology and the genes are, that what underpins it is actually chemistry. So that kind of explains the discreteness there. But we'll talk about that, and we'll hang that whole idea on 3 movies. So what are the movies? Well, the first one is The Imitation Game, which is a recent movie about the attempts to decode and decrypt the messages that the Nazis were using to, send their orders through the air, through the wire, using this Enigma system. Then the second movie is Jurassic Park, which of course we all know, where then there is both the role of the genes and DNA and that the discrete coding in there and computing, and both show kind of the hubris of trying to engineer and manipulate these codes. And then finally Independence Day, which shows the victory of injecting malicious code in the fight against the evil aliens. And it's all a little bit connected to the fight against the coronavirus, but we'll get to that in the end. So let's get going.
Roads? Where we're going, we don't need roads.
It's going airborne.
Well, we used to look up in the sky and wonder at our place in the stars.
War declared! 800,000 children evacuated! German bombs on their way! Get your papers here, fresh off the press! War declared! 800,000
The Imitation Game from 2014 is a movie that illustrates the need to decode the messaging of the enemy. And here we follow the mathematician Alan Turing, played by the famous actor Benadryl Cumberland. And he is trying to develop a way to decode the encryption engine that the Nazis had developed for sending their messages through the Enigma machine.
Enigma is an extremely well-designed machine. Our problem is that we're only using men to try to beat it. Now, what if only a machine can defeat another machine?
Now, what was the Enigma? It was kind of like a typewriter kind of thing, but it encoded messages through this complicated system of different rotors. And you can kind of imagine how this goes, right? So if if you've ever had to or played to develop your own secret language, you might have mapped one character to another character, some sort of substitution system, like, oh, I'm going to write maybe in a different alphabet, or I'm going to shift all the letters of the alphabet to some other spot. like 2001: Space Odyssey. There's the evil computer, which is called HAL, HAL. And if you shift all those letters one step forward, then you go from HAL to IBM. And I guess the name or the association of IBM with HAL is not entirely undeserved, because as a brief side note, we're now talking about the 1940s, the Second World War, and IBM wasn't behaving all that good. They had a German subsidiary, a company by the name of DHOMAG, die Deutsche Hollerith Maschinengemeinschaft mit beschränkter Haftung, that basically sold like a very early form of databases, the so-called Hollerith machines, which were used for tabulating punch cards, sort of. And they were selling those to the Nazis. And the Nazis then used these Hollerith machines to tabulate the data that they were generating for the Holocaust. So, for example, every one of the victims that arrived in Auschwitz and were put to work, they were assigned a number, right, which was tattooed onto their skin. And those were essentially database primary keys into this Hollerith system. And to kind of illustrate this, for example, my dad is named after the cousin of his dad. And he was assigned the number. So that's a primary key in a database of a Hollerith system sold to the Nazis by IBM. So that was happening, but the Nazis were also doing other types of data processing, and especially they were encrypting their messages that they were sending to each other. And for that they used a different system. They were using a system called the Enigma, right? Of course, the riddle or secret or whatever.
Welcome to Enigma. Details of every surprise attack, every secret convoy, and every U-boat in the bloody Atlantic go into that thing, and out comes gibberish.
The half mechanical, half electrical system of substituting letters. And the very simplest thing that you can imagine is basically just like this HAL and IBM kind of shifting of characters. They had these disks or rotors, and they were kind of like cogs or gears with 26 teeth, one for each letter. And they had on one side an input and then on the other side an output. And so every letter was mapped to another letter, just like H in HAL maps to I in IBM, and the A maps to the B, and the L maps to the M, except it was kind of scrambled. And it was scrambled in a way that was totally hard-coded. Each rotor that were initially in the 1920s, they were just sold commercially. The rotors had a kind of a standardized mapping. So for each of the ones that you might buy, the A would map to a Q or whatever. And so that seems kind of simple, right? So you punch a letter on the keyboard and it goes through the first rotor, and the letter that you punch in is mapped to another letter that comes out on the other end of the rotor. Okay, fine. Except once you've punched the letter, then the rotor turns one step. So then the next time you punch the same letter, it has a different internal mapping to a different output letter, and again and again and again every time you punch the letter. And so that's only the first mapping that it goes through. But then it actually goes through another one of those rotors, and then another one. And in fact, like the Wehrmacht had a system where they had 5 of these rotors, and then the Navy and the Abwehr, so the military intelligence, had 8 rotors. So then the mapping already gets super complicated, especially because so these different rotors, like the first one, shifted one letter forward every time you punch a key, and then the other rotors also rotated, but at different speeds. So the mapping was sort of re-scrambled at every step. And then finally, so although the mappings inside each of these disks, that was hard-coded by the manufacturer. So if you knew where they were starting out on a particular day, like if you're super, super lucky, then you could at least reconstruct how then the system was progressing as people were punching keys. But the signal was also run through kind of like a patch board or kind of like a phone switchboard, which you can rewire. Just you can essentially reprogram it every day. And so then that part is totally unpredictable, right? That's not hard-coded by the manufacturer, that they could just decide on the fly. And when you put that all together, then you get a very, very large number of different scrambling directions, basically, that it could go through.
Vibrators. 10 plug board cables. That's
1 million.
1,000 million.
No, I've got it. It's million. Oh, it's in the millions, obviously.
It's over 150 million possible settings.
And in the movie, of course, because we're all idiots, they tell us, well, it's 159 million, which is not an actually existing number. And I guess because they were all mathematicians, they would in fact have said it's 159 times 10 to the power of 18 or 10 to the 18th in scientific notations, which corresponds to a system that has a complexity of about 67 bits in binary as we know it now. And just to kind of clarify sort of, okay, how these things progress. So a bit is, we all kind of know, well, computing, that's to do with zeros and ones. So a bit is like a switch that switches between 0 and 1, so it can occupy 2 states. So when you have 2 bits in a row, that can occupy 4 states, because in combination they can do 0, 0, 0, 1, 1, 0, 1, 1. 4 combinations. And then when you have 3, you have 8 combinations, and then 4, 16, 32, 64, 128, 512, 1024, and so on and so on. And so just for comparison, the Enigma system had 67 bits, and what we now very commonly use is a system that might have, let's say, 256 bits. And just keep in mind, when you compare 67 bits and 256 bits, don't think that, that's about 4 times as much. No, that's not how it works, because so 67 bits, when you add one more bit, so 68, then it is twice as complicated, because you get one more on-off switch. And when you go to 69 bits, it's 4 times as complicated, and so on and so on. So the difference between 67 and 256 bits is just really astronomical. So encryption algorithms have become a lot more complex in the last 70 years. But at the time, it was kind of tractable if you at least were able to come up with some sort of computer that could quickly run through the combinatorics.
159 million possible Enigma settings. All we had to do was try each one.
And that's the big contribution that Alan Turing made, one of the big contributions. So he figured out basically what computing might be, and so he developed this thing called the Colossus, or it has different names, I suppose. And it could run through all the combinations, although that still took a long time. But if they could just restrict the search space at least a little bit, for example, because they knew perhaps what the first messages that were sent in the morning were, and they knew that those would close with
Whole Hockler.
Then they could figure out, well, we know some of the letters already, and that immediately restricts the rest of the search space enormously. And so that's how they could get it to work. So that was his big contribution, the ability to decode super, super complex messages and to kick off computing. And then he went on to basically introduce a bunch of other important concepts, and what the movie, The Imitation Game, is named after is something that's not super relevant right now, which is the Turing test, like this idea that perhaps you might want to try to distinguish between what a real person might say versus what a computer would say. And so then the challenge becomes, well, can we design an artificial intelligence that's clever enough to really imitate human behavior? Or conversely, could humans be predictable enough so that it's very hard to tell them apart from AI? But actually, his more interesting contribution for our purposes is something that came a little bit later in his life and what sets up the next chapter. And this is just to illustrate this very small world of computing and of maths and of biology, because Alan Turing was a
mathematician.
Correct.
However could I have guessed?
Well, you didn't. You just read it on that piece of paper.
King's College, Cambridge.
Which is the same college that Watson and Crick, who are said to have discovered the double helix structure of DNA, were also active. Of course, they didn't quite do that on their own. The work of a bunch of other people is kind of glossed over, and most egregiously Rosalind Franklin. But they were all in very similar academic circles, and they were all also kind of converging on similar ideas. And in fact, Alan Turing was moving later in his career after the war actually towards mathematical biology. So, for example, one of his big contributions there is actually more in what's referred to as morphogenesis. So here the idea is, can we kind of explain mathematically how patterns arise in nature? So how maybe the growth of complex leaves or patterning on fur or stripes or spots or things like that arise through the interaction of different biochemical gradients along tissues. And he was making his contributions to that really very close to the work that was being done in figuring out the double helix. So there's this interesting convergence in time and in space in both computing and genetics. Jurassic Park. So the premise or premises of Jurassic Park are things that only became possible because of the developments that were kind of taking place around the time and a little bit later after the time of the Imitation Game. So starting in the 40s with computing, and then in the 50s with the discovery of the structure of DNA. And much earlier already, of course, scientists had figured out that genes are inherited in kind of discrete packages, which maybe come in different forms or alleles. And so the basic principles of inheritance were not new, but just the mechanics of it and the copying mechanism and the basic building blocks, what they were, became known then. And then over the following decades, 4 or 5 decades, it gradually became clear how to, for example, read then the code. So to decode the information that's encoded in genomes. And that is one of the two things, one of the two ideas that are being developed in Jurassic Park. And actually the other one is computing and the hacking and the manipulation. So whereas in the Imitation Game, the English are very hesitant actually to do almost anything with the information. Certainly they weren't going to send encoded messages, and they wouldn't even do unlimited reaction to what was being sent, because obviously then the Nazis would know that the English knew, and that was a problem. But in Jurassic Park, that goes a lot further. So they, in this movie, have figured out, first of all, how to clone and de-extinct dinosaurs.
Using sophisticated techniques, they extract the preserved blood from the mosquito and, bingo, dino DNA. A full DNA strand contains 3 billion genetic codes. If we look at screens like these once a second for 8 hours a day, it'd take 2 years to look at the entire DNA strand. It's that long. It's full of holes. Now that's where our geneticists take over. Thinking machine supercomputers and gene sequencers break down the strand in minutes. And virtual reality displays show our geneticists the gaps in the DNA sequence. We use the complete DNA of a frog to fill in the holes and complete the code. And now we can make a baby dinosaur.
And they built a couple of fail-safes into it, like against reproduction.
How do you know they can't breed? Well, because all the animals in Jurassic Park are female. We've engineered them that way.
And they had also kind of hacked into it, basically what you might call a logic bomb. So a system to make it so that, or kind of like a kill switch, really.
The lysine contingency is intended to prevent the spread of the animals in case they ever get off the island. Dr. Wu inserted a gene that creates a single faulty enzyme in protein metabolism. The animals can't manufacture the amino acid lysine. Unless they're completely supplied with lysine by us, they slip into a coma and die.
So a system to make it so that these dinosaurs could always be controlled biochemically, let's say. And actually that hacking is kind of mirrored in computer hacking that's happening at the same time. So there's really two hackers in this movie. There's the young girl.
I'm a hacker. That's what I said. You're a nerd. I am not a computer nerd. I prefer to be called a hacker. Who,
in the end, saves the day, or at least in one of the scenes.
It's a Unix system. I know this. It's all the files of the whole park. It tells you everything.
So she's like the white hat hacker. And on the other hand, there's the black hat hacker who has first developed the whole security system and written very large amount of code, but then put some backdoors in there so that he could take advantage of the system.
Access main program. Access main security. Access main program grid.
You didn't say the magic word.
Please! God damn it! Hate this hacker crap!
And what is being played up in all these different scenarios, both in the Imitation Game and here, is the very, very large amount of data or combinations that would have to be evaluated and sifted through to get at what you're interested in, right? In the Imitation Game, it's the encoding and the very many different permutations in that. And here it's the enormous size of the genomes that they are manipulating and the enormous size of the whole code base of the security system, which had manipulated. So in all these cases, these are very, very complex systems. And the movie Jurassic Park is actually kind of a parable that is supposed to warn us to not have this hubris where you might think that you can control this complexity, but in fact you can't.
Next time it'll be flawless.
It's still the flea circus. It's all an illusion.
When we have control again.
You've never had control. That's the illusion.
And maybe a bit more humility would be in order.
Gee, the lack of humility before nature that's being displayed here staggers me.
Because these systems are far too complicated to just tamper with, right? We're being taught this by a character who's very similar to a character in the next movie, and both played by the same actor, Jeff Goldblum. And in Jurassic Park, he plays the role of the kind of cynical rock star scientist, and he plays kind of a different role in the next one. And he is the one who constantly is emitting these warnings about, you can actually not really control these very complex systems. And then in this movie, that is all kind of illustrated with reference to what was then very fashionable, namely chaos theory.
Still not clear on chaos.
It simply deals with predictability in complex systems. The shorthand is the butterfly effect. A butterfly can flap its wings and be king, and in Central Park you get rain instead of sunshine.
chaos theory is kind of this idea that even with mathematical functions that are understandable and sort of regular in their own way, but when they feed back on each other and maybe work in some sort of nonlinear way, then the outcome is actually totally unpredictable and for all intents and purposes seems basically random. So which is actually almost the exact same thing as the operation of the Enigma machine, which has just a very regular mechanism and regular data goes in and something totally scrambled comes out. And in fact, chaos theory is also applied in cryptography. So these two things are totally connected. So in Jurassic Park, the lesson is, well, don't try to tamper with this complexity and don't try to inject your own code into these very complex systems, because who knows what kind of downstream effects that might have.
You have meddled with the primal forces of nature, and you will atone.
And that risk is very well understood in the Imitation Game, but it's not so well understood by the people in Jurassic Park, to obviously disastrous effect.
A historic and unprecedented event is occurring. The question of whether or not we are alone in the universe has been answered.
This is so cool.
More ships have just arrived over India.
In the movie Independence Day, the enemy is a civilization of hostile space aliens. The Harvesters, who are a bit like locusts. And as a terrifying aside, there's right now, in addition to the pandemic and also rivers running red.
Residents in eastern China woke up early this week to find the river that runs through their city had turned blood red.
Let's say China. 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 You go over to China. 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 You take China.
China.
China. I love them. China. 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 I have to have my China.
There's also locusts that went into this swarming migratory state.
What the cutting locust left, the swarming locust has eaten. What the swarming locust left, the hopping locust has eaten. And what the hopping locust left, the destroying locust has eaten. It is now time for people to repent. This is not normal.
Terrifying the shores of Lake Turkana, I guess I saw online. But these, the aliens from Independence Day are space locusts, and they are absolutely ruthless. When asked, they are not particularly sanguine about the prospect of having peace with the Earthlings.
I know there is much we can learn from each other if we can negotiate a truce. We can find a way to coexist. Can there be a peace between us?
No peace.
What is it you want us to do?
And when that became clear, the Earthlings were also not particularly interested in making peace with the space locusts.
Nuke them. Let's nuke the bastards.
So, well, what actually happened? Well, initially they simply approached the Earth and, the Earth's various detection systems kind of noticed that there's something big behind the moon. And then there is starting to be interference in the communication systems used by various nations. So what seems to be happening is that all the signals that are getting bounced around the different communication satellites, so just for TV and stuff, those are used as kind of a carrier signal for their own embedded and encoded messages.
I got a lock on the pattern of that signal, and so we can filter it out. But if my calculations are right, it's going to be gone in like 7 hours anyway. It's reducing itself every time it recycles, so eventually it's going to disappear.
And who discovers this? Well, if it isn't our good friend Jeff Goldblum, who is again back as a mathematician, and he's the first one to kind of figure out that there is some sort of signal embedded in the satellite signals. He works for a cable company as kind of like a clever guy who fixes their signals. And he figures out that the interference, there's actually some regularity to it. And we very, very briefly see something that, of course, makes zero sense. But we see him walking around with a printout that has zeros and ones on it. So the binary code, like we just talked about, which, by the way, is totally meaningless, right, by itself. Those are just switches, and only if you understand what they code for can you draw any conclusions. But of course, Jeff Goldblum is very, very smart. And so he figures out that there's some sort of regularity in the code. I guess it's some sort of number sequence. And he finds out that it seems to be working its way down. The sequence, I guess, is getting somehow shorter or something like that. So there's a countdown clock in it. And of course, he expects the worst, and he thinks that perhaps when the clock, once the clock has totally run out, something bad is going to happen.
In approximately 6 hours, the signal's going to disappear and the countdown's going to be over.
And then what?
Checkmate.
Oh my God. Oh my God.
So he somehow has deciphered the code, and that must be very difficult because you need to know a lot before you can decipher code like that. So, for example, in the case of the Enigma, right, in the Imitation Game, what the Allies, first the Polish and then the English and others, got their hands on was an actual Enigma machine, and basically the earlier computers that they were using were kind of like reverse engineered Enigmas, or they had the same kind of rotor system, but then sort of they ran through as many of the different combinations that they could to try to figure out which one was the right one. So there was a whole bunch of reverse engineering of the signal in that. And actually in DNA sequencing, there's a kind of reverse engineering in that as well, because the way these sequencers now actually have always worked, but nowadays as well, they all differ a little bit. But what they'll do is that they take a DNA strand, a single strand, and then that strand functions as kind of a template. And so then one after the other, all of the different DNA letters are basically tried out as a kind of a very simple machine, again, go through all the possible combinations that can go on each position. So you start at the first position of the strand, you try out, okay, does it fit an adenine or a cytosine or a guanine or thymine, and so the letters A, C, G, T, and one of these four is going to stick. And then in some way or another, you're going to pick up which one that was, and there's different biochemical tricks for that. And then you move on to the next letter. So there again is a kind of reverse engineering. And here in this case, I guess what we are supposed to understand is that the reverse engineering has been made possible by the things that are secretly being stored in Area 51. So this then kind of the trick here is that there was these flying saucers that supposedly crash landed in Roswell, New Mexico in the 1950s. And then those would have been stored at Area 51. and somehow that would have allowed Jeff Goldblum to figure out the coding system in the span of 24 hours, which is somewhat implausible. But that's apparently is what he did. And then what he's going to try to do next, and so here the Jeff Goldblum in this movie is totally different from the Jeff Goldblum in Jurassic Park, because in Jurassic Park he's very, very pessimistic about our ability to interfere in these very complex systems at all, because it's all chaos and dangerous and scary, and we should have more humility. But here he feels really differently, and he thinks, well, first of all, apparently he can figure out really the coding of these bits that he's been detecting, so that that's already almost impossible to reverse engineer. You have to basically understand how these aliens encode numbers and other symbols, and even that there's like a bunch of different choices which are basically equivalent between different computer systems among Earthlings. So I'm sure the aliens also have their own arbitrary choices to make. And then he has to design an interface that somehow allows him to connect his Macintosh System 7 laptop to the alien operating system. So I don't know if there's like Ethernet or something for that. And then he also has to actually code the whole virus in this newly discovered alien programming language. And then
if we plant a virus into that mother ship, it's going to then filter down into all the corresponding ships below.
Then the next step is to log in on the mainframe of the mothership. And as in the classic trope of all these movies, there's a few keystrokes. And then we're in. It's either that or it's generally, like the scene from a really, really bad but enjoyable movie, The Lawnmower Man, where in the climax of the movie, the protagonist has uploaded himself into virtual reality and tries to log in on the Vos system, and then this happens.
Access denied. Access denied. Maintenance line. Access granted.
Finally, access granted. Yay, we're in. Okay, and then next step is now we have to upload the virus. And I guess hopefully there's enough bandwidth for that. And not only is it just a virus that messes up the system of the aliens, but there's also still time to embed a little animation of a skull and crossbones in it. And also to make the virus interface with the, the sound system on the mothership, so that they can also, humiliate them a little bit with this message. But finally, it all works, and yay, they have been able to actually crash the system, the software of the mothership, which then makes it drop the shields, and then the Earth Defense Forces can take down all the other gigantic spaceships, the city destroyers. And by they, I mean Jeff Goldblum, and of course...
Drums, please!
Will Smith. And slightly sad news related to that. I just read just now that DJ Jesse Jeff has also been diagnosed with corona. So thoughts and prayers for Jesse Jeff, I suppose. But anyway, so Will Smith and Jeff Goldblum managed to make it work. And then they have to get out of the mothership. And here there's actually a tiny little homage to Jurassic Park, because in Jurassic Park there's the scene where Jeff Goldblum is incapacitated and he's being loaded onto a jeep, and then just the T-Rex appears, and then he is being saved by two other characters who then drive him off, and then he says,
"Must go faster."
And then in Independence Day, when he and Will Smith are flying out, trying to get out of the mothership, he also says,
"Must go faster. Must go faster. Go, 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 go."
So the movies are totally connected, obviously. Except, of course, they make entirely different points. So in Jurassic Park, the message is, or the warning is, that, you are meddling with the forces of nature and you shall atone, and disaster ensues. And in Independence Day is the exact opposite. It is all-round success against all odds, and humanity is saved. And I guess we are kind of facing the same challenge, except slightly less apocalyptic, with the coronavirus. We've been able to decode it, and us, but we, people more competent than I am, and maybe also than you are trying to come up quickly with medication, treatments, and policies, and all the rest to deal with this pathogen. And one of the tricks that is being tested out right now, and we should have more news in the coming days, and that is basically the same trick to try to inject some malicious code into the genome of the virus, hence the theme of the podcast. So what is being tested right now, what is generally being seen as probably the most hopeful medication, worldwide, so separate from the hydroxychloroquine kind of stack with the Z-Pack and the zinc, but which is all something else. What is now being regarded as the most hopeful, also by the World Health Organization, is this drug called remdesivir, which we discussed briefly in a previous podcast about the race for the treatment. So what does this drug do? Well, it is this molecule, the remdesivir molecule, is basically an analog of one of these 4 DNA letters, right? So it is an analog of adenine. And so the trick here that is being tried out is as follows. The virus wants to replicate itself, or has evolved to attempt to replicate itself by using the machinery of the host, so that's us. And then what it does is, it has a single strand of code, right? Its genome. It wants to make copies of that, and so there's then a kind of enzyme called a polymerase, which attempts to one by one insert the complementary letters into the template of the viral genome. So again, these letters A, C, G, and T are plugged in one after the other in the right spot. And so what this drug does is, it looks biochemically just enough like adenine that the polymerase of the virus might accidentally insert it into the growing copy. But when that happens, then the rest of the replication procedure stops. And so then no further copies are made. And what it looks like might be the case is that this drug is just specific enough that it halts the replication of the viral genome, but not our own copying processes in our own cells, which we would ideally just like to continue as normal, wouldn't we? So that's being trialed right now. There's actually a whole bunch of trials going. One of them is actually split across severe and mild cases. And the severe cases, the experiment must have ended on April 3rd. And I guess we're kind of hoping that we will have a release of the results very, very soon, next couple of days. Maybe we already know when you're listening to this. So let's hope for the best for that. And let's see if we can maybe defeat this enemy using the old trick of a malicious code injection. So let's hope that works, so that, now that summer is coming up, maybe all the restrictions can be lifted a little bit. And if not, well, then at least there's plenty of time to both record and listen to podcasts. So we'll just keep doing that. Well, we'll do that either way. And whether that also means that I'm going to be making more podcasts on my own, I guess it depends a little bit on the feedback. So this is an experiment. Feel free to let us know that you really liked it, and you can phrase that however you like it. Or if you think, well, yeah, maybe not. I guess that kind of feedback is also welcome, but just please be a little bit more gentle. Well, how can you tell us? So you can tell us in a bunch of different ways. There's a Twitter account, GOT_Academy, where you can reply or send, follow, and we might follow back if you want to message us for something. So that works. Of course, there's a Patreon. So patreon.com/GotAcademy. And of course, those messages are from paying customers, so they get preferential treatment. I'm sure you understand. Because so far, at least at time of recording, we're still living under capitalism, but who knows? And there's Facebook, and I guess you could also email geelkid@gmail.com. And I guess that's about it. All right. Bye everybody, and be safe, and avoid each other, and stay healthy, or heal quickly if you are experiencing something bad. And talk to you later. Bye.
You so totally rock, Squirt! So give me some fin. Noggin. Dude.